And now we can have the second research presentation. So I believe the presenter will be Franz from TU Berlin, right?
Yeah, exactly.
Yep. So he will be presenting a paper called Paris, a playground for network interrupt experiments on real-time embedded system in the IoT.
Exactly.
Yeah.
So hello from our side. Hello and welcome to our presentation of Paris. My name is Franz and my colleagues and I are all researchers or students from the Technical University of Berlin, and we're pleased to be able to present this project here. Oh, and I think I should try to make this here go away. Okay. We'll begin with our outline. So we'll start with the motivation, then we'll talk a bit about our approach to Paris. Afterwards, we'll show you some experiments using our playground, and this will also conclude our talk. We begin with the motivation. So we live in a world full of real-time systems and, of course, real-time operating systems, especially in the industry, and that's why we have this robot arm on the right. And that's because they have many advantages. They're lightweight, they can run on basically every system, and they can give us guarantees on when a certain task finishes, which is really important for industrial applications. Now, in the late 2000s, the Internet of Things really took off, and more devices, including those real-time systems, got connected to the Internet of Things. And now the question is, what are implications or effects of this? And for this, we need to look at how network packets are handled on those systems. We assume that we only look at systems where the NIC, so the network interface controller, and the microcontroller are separated, and event handling is done by interrupts. I mean, there are other systems, but this is what we are looking at here. In the diagram, you can see basically that packets arrive from the internet at the network interface controller, which in turn interrupts the microcontroller. And now imagine you have some critical task running on your microcontroller, which has to finish in a certain amount of time. And now when an interrupt happens, the execution shifts to the interrupt service routine. And the more interrupts happen, the more execution time is spent in the interrupt service routine. And this might even starve the critical task. So the question is now, does this really happen? So do network interrupts really pose a threat to the real-timeness of those systems? And the second question is, how can we conduct research on this? So given some microcontroller or some system, some code with a critical task and some analysis scenario, how long will it take? Basically, the first question was already answered in our first reference. So really, it depends whether you're careful with your task priorities and what system you're looking at. And the second question still remains open, and this is basically the topic of Paris. And our goal is now to create a playground where we can put in some source code, which we want to be tested, which contains some critical task, define some kind of analysis scenario. So what kind of network interface do we want to use? What kind of loads do we want to use? And get some numbers out, such as the execution time or number of interrupts independent of the load and of the system. And now Jonas will talk about how we approach this problem.
Thank you, Franz. I hope everyone can hear me well. First, in our approach, we want to talk about the operation of the playground. Yeah, thanks. The operation of the playground. The general procedure we had in mind for user operating the playground. And first, the setup of the microcontroller has to be done. And then the user code can be inserted to the program code of the playground. And this user code is the test subject, the code to be tested. After that, the user can configure a network traffic load. This can either be a uniform load or a random load, or it can be a pre-recorded network trace. And this can then be parsed from PCAP. After that, the user can configure a network interface controller, a NIC, and flash it all to the microcontroller, execute, and then in the end copy the result for analysis. For the network interface controllers, we have different models that can be configured. The most basic one is this simple NIC model, where we just model the total duration per packet as some length-dependent delay times the packet length plus some length-independent delay, which is some overhead that has to be done for every packet. Obviously, in the real world, there are more advanced implementations of NICs that use interrupt moderation. And interrupt moderation allows for the CPU to decide whether it wants to be informed about new packets right away or later. And our playground supports NICs to be defined with either a counter mode, a timer mode, or a combination of both out of the box, which we will refer to in the following as mixed mode. The NIC implementations with a counter mode work that way that the NIC does not trigger an interrupt right away when a packet arrives, but it will wait until a specified number of packets have arrived and then trigger one single interrupt for them all. And until that point, the packets are stored in a buffer. And therefore, the running test code or the running CPU is not interrupted every time. After an interrupt has been invoked, the counter and buffer are being reset. The NIC implementations with the timer mode work differently. There, when a packet arrives, it gets written to memory and no interrupt is invoked. Instead, a packet delay timer is set, and this packet delay timer starts running. If another packet arrives before this packet delay timer has run out, then the new packet also gets written to memory, and there's still no interrupt being invoked, and instead the timer gets reset and starts running again. When there's no more further packet arriving until the packet delay timer has run out, then the interrupt gets fired. It's one interrupt for all of the packets that have arrived before. And this can obviously lead to the situation where there are always interrupts coming in a constant way that the packet delay timer gets reset and no interrupt gets fired. That's why the third option we have in our playground is to combine timer and counter mode to ensure that an interrupt gets triggered eventually. So now I want to come to the network traffic scenarios as load. And we implemented multiple load generators to offer flexibility. We define a load scenario as such that it's the arrival of packets with corresponding timestamps over some observed time. And our playground offers network traffic scenarios either to be defined as uniform loads with a constant receive frequency, or as random loads, which we will come to in a second, or as user-defined or pre-recorded loads, which we will also explain a little bit further. So starting with the random loads, we used the Poisson distribution to model random loads. We assume that the incoming packets per interval are Poisson distributed, and therefore the inter-arrival time between these packets, which is important to our implementation, is exponentially distributed. So problem is that there is no exponential distribution which you can sample from on a microcontroller. So you can only sample from uniform distributions, from a uniform distribution. And we did that, therefore, and we used inverse transform sampling to get to our exponential distribution and to be able to sample our inter-arrival time that way. The user-defined loads are also possible. Our playground allows for recorded network traffic scenarios to be replayed, and those network scenarios have to be provided as packet captures. These packet captures can be parsed by a script provided by us to the inter-arrival times, and these inter-arrival times can then be automatically integrated into the code. And this allows for custom reproducible loads, but the PCAPs have to be of a sensible size, obviously, because microcontrollers only have limited memory. So the PCAP size has to fit that memory of the microcontroller. And in the end of the approach, we want to quickly talk about the prototype implementation. We implemented the playground on the ESP32, and that uses FreeRTOS. And the ESP32 has a dual core, which is really nice for our playground because we can run our development playground with the included network simulation on one of the cores and the test subject on the other, where it can run unhindered until interrupts from the network simulation interrupt the test subject. And we used this implementation to conduct some experiments, and Nick is going to present them to you.
Thank you, Jonas. We have selected 4 experiments from our tests to present to you. First will be 2 validation experiments, which will then be followed by 2 practical examples. For all but the last experiment, the Poisson distributed random load is used. And the user code we used here for these experiments is just a simple large summation. In the first validation experiment, we take a look at how the packet delay timer influences the execution time of the user code, measured on the left-hand y-axis, and the number of interrupts measured on the right-hand y-axis, while using the mixed mode. Our expectation here was that a longer packet delay timer results in shorter execution time and less interrupts, because more packets are grouped into one interrupt. In this plot, we see that our expectation is indeed fulfilled. In the second validation experiment, we have plotted the execution time for 3 different parameters lambda for the Poisson distributed random load generation in counter mode. We do this because we want to show that the counter mode scales linearly with the network load. In the legend, you can see the 3 lambda values, the last 2 being twice as big as the previous ones. A higher lambda value corresponds to a higher network load. The initial differences between the execution times are plotted here as vertical lines between their respective plots. And these distances stay roughly the same along the counter thresholds on the x-axis. The difference between the second and third lambda's execution times is roughly twice as big as the difference between the first and second lambda's execution times, to be precise, 1.93. So a doubling of the network load results in a doubling of the execution time. For the first practical example, we used the playground to investigate the reasons for interrupts. We measure the influence of both counter threshold and the packet delay timer on the execution time. Each dot here represents one result of the playground being run to test user code with a Poisson distributed load in mixed mode. The color of a dot represents the distribution of the reasons of interrupts. Blue for more timer interrupts, yellow for more counter interrupts, and green for a balance between the two. To exploit the benefits of both timer and counter mode, we want both to cause interrupts, that is, land in this balanced area. For the second practical and final example, we are using the recorded loads functionality of the playground with the mixed mode. 2 network load scenarios were recorded and are compared here. Audio streaming using Spotify, which was rather bursty and is colored blue here, and a Zoom video conference call, just like the one we are in right now, which had a more continuous packet arrival pattern, colored orange. For each, 2 things are shown here. First, a line for the execution time of user code measured on the left-hand y-axis in the face of the given network load scenario and against the packet delay timer on the x-axis. Second, also a histogram for each network load. On the x-axis, the packet inter-arrival time in the recording for the bins of the histograms. On the right-hand y-axis, the number of packets with such a delay since the previous packet. The apparent third histogram you see here is just the overlap between the 2 histograms. For both loads, we can see that the execution time drops off noticeably when we increase the packet delay timer past the inter-arrival times where the majority of the packets fall in, so where histograms have the largest bins. The bursty Spotify load benefits more from doing so, whereas the continuous Zoom load almost resembles a Poisson distributed load. So in conclusion, we have seen that our playground enables researchers to conduct experiments in the context of network interrupt simulation in real-time scenarios. It offers multiple load generators, including random and custom pre-recorded settings, as well as logging functionalities. And it was validated through a series of tests. For future work, one might add more and more complex NIC models and also create a repository of these network recording PCAP files. This concludes our talk. Thank you very much for your attention. And we are now very happy to answer any questions you may have.
Thank you very much. And now we can take some questions. Do we have any question from the audience? So for asking questions, please feel free, just unmute yourself, or you can use the chat to type out your question. So if no question, then
Hi, I don't have any question, but I just want to say I think the presentation is very good and very informative, and the presentation is also connected with some practical example. And I just want to say thank you for the presentation.
You're welcome. Thanks for the for that.
yeah, it's definitely a great presentation. And so maybe I missed it in the slide, but so do you have the tool available online as open source for now?
We didn't put the link on the slide, but in our paper, you can basically find a link to a repository where we'll publish the code. It's not published right now. We're still in the process of publishing it and cleaning it up. So just keep an eye on, on that link, basically. The link should be on the last page of the PDF.
Yeah, thank you. And you mentioned that there will be continuous effort to maybe include more feature and more functionality to the code in the future, right? So I think that will also help the community a lot because many people are working on the benchmarking and performance testing. So I think this kind of tool can really help them to simulate different network interrupts during the test, during the testing process. And do we have other questions from the audience? Okay. So I think it's because your presentation was too crystal clear. So there's not too much question from the audience. And I think we still have a few more minutes until the next presentation, which will be the keynotes. So I think it would be good for people to take a short washroom break, and we can restart in maybe in 2 minutes.